In all of our previous torque examples, the forces were always perpendicular to the radius of rotation. Now this is clearly the way to get the most torque out of a given force. That is, the entire force is contributing to the torque. But what if this is not the case? That is, what if the force is at some angle other than 90 degrees? For example, in this case, we can see that the force is not pushing perpendicular to the radius of rotation. So, part of this force is contributing to the torque, but not all of it. So the resulting torque will be less than just multiplying R and F. Now this is the point where we go back to our original definition of torque. That is, tau equals R cross F. And we look closer at this cross operator here. In cases where the force is perpendicular to the radius line, we just multiplied the R and the F. When this is not the case, we have to consider an adjustment to account for the lesser torque. Now there are two ways to deal with this situation. One way is to use components to determine the portion of F that actually contributes to the torque. So we can break up F into two components, Fx and Fy. And we can see that Fx is the component that's perpendicular to that radius, and therefore contributes to the torque, while Fy doesn't contribute at all to the torque. So let's focus on Fx, the component contributing to the torque. And to do this, we need to determine some angles involved. That is, if this angle is 30 degrees here, then this angle up here would be 90 minus 30 equals 60 degrees. And then this angle up here would be 90 minus 60, or back to 30 degrees. So our component Fx would be F cos 30. And we can plug that into our trusty equation for torque, T equals R cross F, where R is, in this case, the length, and F is our Fx. And we can replace that Fx with F cos 30. So we've now adjusted for that angled force. Using this method makes a lot of sense in that we can see that this is the component that contributes to the torque. But the method itself involves a lot of playing with angles to get there. The other common way to determine the torque caused by F is to modify the radius rather than the force. Now we can do this by extending our force vector, and then we can draw the radius line from the pivot point so that it intercepts the force vector at a 90-degree angle. We could also visualize this by drawing a circle right around our pivot point, intersecting the force vector right here on the edge. The radius of this circle is our adjusted radius. So either way, we can label this as our modified radius of rotation, and we'll call it Rx. And since these lines form a nice right triangle, we can see that our modified radius is L cos 30. So using our trusty torque equation, tau equals R cross F, with R being replaced by Rx, or L cos 30. And F is just the force this time. No modification required there. And again, we've determined the torque caused by this force. So let's compare our results. L times F cos 30 and L cos 30 times F. The resulting equations present in a different order, but they're in fact the exact same. So which method should you use when faced with a torque problem involving a non-90-degree angle? Well, method 1 is a great way to visualize what's going on here. It's easy to look at the components and recognize that only the perpendicular component actually causes torque. Given that, While it's easier to visualize using method 1, the geometry, that is, determining all the angles, can sometimes be a bit confusing this way. Method 2 may be a little less intuitive from a conceptual point of view, but we often find that determining the angles using this method is a bit easier. So with these general ideas in mind, attack your problem using either method. They'll both give you a correct result.